So here's a quick example involving nodal analysis, but this one's a little different in that we do have some nonlinear components, inductance and capacitance, and what they're asking us to do is to use nodal analysis to determine what the voltage across the 4 ohm resistor is. So here's the 4 ohm resistor, and so that's what we're going to try to calculate. So first we want to first thing we want to do is convert everything to admittances instead of ohms or impedances. And so to do that, for resistances, it's just the reciprocal, right? So this one, instead of 4 ohms, the reciprocal of that is 0.25, and that's going to be Siemens. And for reactive components, it's the negative reciprocal. So the negative reciprocal of this, 5, if you do the reciprocal of that, is going to be 0.2. So this is going to be negative 0.2 J Siemens. And then same thing for this capacitance here. If we have 2, the reciprocal of that, negative reciprocal, that'll be 0.5 J Siemens. So now we have everything in admittance, and so we think that might make it a little easier to write. So let's see what happens. So the first thing we want to notice is we have a node here and a node here, and so we're going to call this node node 1, and we're going to call this node node 2. And we notice that actually this is the extent of the node here. So the voltage there, we're going to say it should be V1. And then likewise, the extent of this node goes all the way here. And so we're going to define the voltage here as V2. So this being the case, what we're actually looking for then is V1. So V1 is going to be the voltage across the 4 ohm resistor to ground. So if we can find that, then we have solved the problem. So let's start writing some nodal equations in. We'll start with node 1, which is the red node. And as we go down this path, we see here that we have this current source, and we're summing up all the currents going in and out of the node, right? So we want to define leaving the node as positive. So that being the case, this current is shown entering the node, so it'll be a negative, it will be a negative 3 at an angle of 30. So again, I lost my highlight there. That's this component here, contributing to that. And so next we have the resistor. And let's do that in a different color. Let's do that in red, since that's really what we're looking for. So the resistor here of interest, and so that's going to just be the admittance times the voltage to give us the current. So in that case, it'll be plus 0.25 times V1. And then finally, we've got this component going in between. Make that a different color here, this component here, and that's going to be the differences in the voltages times that admittance. So when we write that out, we've got a negative 0.2 J times V1 minus V2. And so that's the 3 paths going in and out of there, so we should be able to set that equal to 0. Let's do that here. My pen will work right. So that should be 0. All right. So now we want to go over to node 2, which we designated as blue. And so when we look at this one, again, we have another current source. Again, leaving the node, we've set as positive. So this is going to be a positive 5 Let me get green here. So I can get my everything straight here. 5 at an angle of 30 degrees. And then again, we have this capacitor here. And so the capacitance there will just be the admittance times the voltage. So in this case, that's going to be plus 0.5 J V2. And then again, the purple, which we already highlighted, again is going to be the difference between those two. So that's going to be minus 0.2 J times V2 minus V1 this time. And again, summing all these up should equal to 0. So now we notice that we have some things, some terms that we can combine and simplify this. So let's do that. So looking at this first equation, if we were to rewrite this, we could say then that it's V1 times 0.25 minus 0.2J, and then that's going to be plus V2 times 0.2J, and that's all going to equal to 3 at an angle of 30 degrees. Okay, and same thing here. We can simplify this equation, and we're going to have here V1 times 0.2J, and then that's going to be plus V2 times 0.3J, and that's all going to equal to minus 5 at an angle of 30. So now you can see we have a combination of polar coordinates and imaginary terms. So we want to rewrite these. We want to get it all consistent. So let's put it all in polar form. So if we do that, let me redesignate then my red node equation then will become V1 times 0.32 at an angle of minus 38.7 degrees, and that's going to be plus V2 times 0.2 at an angle of 90 degrees, and that's all going to equal to 3 at an angle of 30. And then likewise, we can do our blue equation. We can write it totally in phasor form. And when we do that, we get V1 times 0.2 at an angle of 90 degrees plus V2 times 0.3 at an angle of 90 degrees. And that's going to equal to minus 5 at an angle of 30. So now we basically have two equations and two unknowns. So there's a number of ways that we could solve that. So in this case, we really only want V1, or need V1. So we can write the equation for that, or just the general vector form. If we do the general vector form, it'll be 0.32 at an angle of minus 38.7, 0.2 at an angle of 90, 0.2 at an angle of 90, 0.3 at an angle of 90, and that's going to be times V1 and V2, and that's going to be equal to 3 at an angle of 30 and minus 5 at an angle of 30. Again, that's just an array there. So again, we can plug this into the standard calculator and solve for these, and when we do, we will see that V1, again, solving just this, so you divide this into this on your scientific calculator if it has the matrices operators. And what we come up with is 15.2 at an angle of 83.2 0.2 volts. So this would be the voltage across the 4 ohm resistor, is what they asked for.